we have looked at two equations. The entropy change for the universe is the sum of the entropy changes for the system and the surroundings. And the entropy change for the surrounding at constant P and T is equal to negative of the enthalpy change for the system divided by the temperature. So we can put these two equations together. Instead of writing delta S surroundings, we'll put this in there. So we'll get delta S for the universe is equal to delta S for the system plus negative delta H system divided by T. And then I put this in here because I always forget what to do next. Multiply by negative T. So we're going to multiply both sides by negative T. So on the left, I get negative T to delta S for the universe is equal. And I'm going to reverse the order here, because when I multiply this one by negative T, I end up with positive delta H. Because this T is going to cancel out that T, and the negatives are going to cancel out. And then I've got delta system times negative T, and so that's going to be negative T times delta S for the system. Again, this is one of those derivations that I do not expect you to remember or even necessarily totally understand as I do it, but I'm showing it to you just because this is how scientists do things. And it's important to understand that we're not just like making up these equations, right? We're not just making stuff up here. So if we drop the cis subscript, so this was cis and that was cis for the system, and we just tell ourselves, well, we're just going to remember that quantities that don't have a subscript, we're talking about the system. So now we've got the change in entropy for the universe, and it's related to the change in entropy for the system. Well, here's a new quantity, the Gibbs free energy, and that has the symbol G. Gibbs free energy is equal to the enthalpy minus the temperature times the entropy. Okay, so what is the change in Gibbs free energy? Well, delta G is going to equal the change in H minus T delta S. It's the change in this and the change in that, but the temperature is constant, so we're not changing the T, just the S. So delta H minus T delta S. Oh, well, that's this thing right here. So delta G is negative T times the change in entropy for the universe. Change in Gibbs free energy for a process at constant temperature and pressure, proportional to the negative of the entropy change for the universe. So Gibbs free energy is also a criteria for spontaneity. If the Gibbs free energy is negative, that means the change in entropy for the universe was positive, spontaneous process. Gibbs free energy is also called chemical potential. Chemical potential, it's equivalent or analogous to mechanical potential energy. So mechanical systems tend towards lower potential energy, right? Objects fall to the ground, they don't just spontaneously levitate. They fall because that lowers their potential energy. Well, chemical systems are also going to tend towards lower potential energy, but lower potential chemical energy, lower Gibbs free energy. So if delta G is less than 0, it's a spontaneous process. Delta G being less than 0 means that delta S for the universe is positive. Any questions? The whole positive negative thing can get really confusing. This allows us to calculate delta G only referring to the system. It's really hard to quantify things in terms of the surroundings because technically it's the rest of the universe, right? So it's nice to be able to calculate things just in terms of the system. So we can calculate delta G if we know delta H and delta S for the system. Delta H was covered back in chapter 7, and we just learned about delta S. So if we're looking at free energy, so Gibbs free energy being higher, and this is concentration changing. So here we have pure reactants, here we have pure product. It's going to go somewhere in the middle, right? It's going to be an equilibrium, and we learned about the equilibrium constant and the reaction quotient, right? So if Q is equal to K, the system is at equilibrium and it's not changing. If Q is less than K, that means that the change in free energy is going to be negative, and that's a spontaneous reaction towards the products. On the opposite side, this would be a spontaneous change towards the reactants. Again, a decrease in Gibbs free energy. Oops. So there's different combinations of positive and negative, which kind of gets back to the question earlier. So if we have an exothermic reaction that has a positive change in entropy, so delta H is negative, and the change in entropy for the system is positive, then delta G is going to be negative at all temperatures. Doesn't matter what the temperature is. If we have delta H being positive, an endothermic reaction, so energy is coming in, and delta S is negative, we have a negative change in entropy for the system. This is going to be non-spontaneous at all temperatures. Case 3, delta H is negative and delta S is also negative. So delta H is negative. The sign of this one is going to be positive, but whether our delta G ends up being positive or negative depends on how big the temperature is. So this will be spontaneous at low temperatures and not spontaneous at high temperatures. And then the opposite thing where we have both of those being positive, we have energy going in and a positive change in entropy, and this is going to have the opposite relationship to temperature. This will be non-spontaneous at low temperatures and spontaneous at high temperatures. So this is the book's attempt to summarize this. So when delta H and delta S have opposite signs, you can figure out what's going to happen. When they both have the same sign, either both negative or both positive, then the spontaneity will depend on the temperature. And you can find the temperature at which the spontaneity changes by setting delta G equal to 0. That's the point where it goes from positive to negative, right? So from non-spontaneous to spontaneous is where delta G equals 0. And then you can solve for T. So you've got that equation, delta G is equal to delta H minus T delta S. Well, if we say, okay, well, where is that zero? We know delta H, we know delta S, we can find out the temperature at which it changes, and we can say above this temperature it's this thing, and below it's the other. Consider the reaction C2H4 plus H2 to make C2H6, and we're given delta H and delta S. Calculate delta G at 25 degrees Celsius and determine whether the reaction is spontaneous. Does delta G become more negative or more positive as the temperature increases? Delta G equals delta H minus T delta S. So we're told what delta H is, right? Negative 137.5 kilojoules, but we also have entropy in here, which is joules. So I'm going to do the fast change into joules, right? 10 to the 3 instead of kilo. So that's delta H minus the temperature in Kelvin. 25 plus 273, 298 Kelvin, times delta S. Delta S is negative 120.5 joules per Kelvin. So the kelvins cancel out. We thought ahead so that the joules and joules are the same. If this is kilojoules, you can't subtract joules. They have to be the same unit. So negative 137.5 times 10 to the 3 minus 298 times negative 120.5. Negative 101.591 joules. So this is a big number, right? And so we would usually use kilojoules to express that. So that's negative 101.591 kilojoules. Negative 101.6 kilojoules. Delta G for that reaction. Is it spontaneous? Yes. Delta G is negative. It is spontaneous. So any questions about that part? So the next part is, does delta G become more negative or more positive as we increase the temperature? Well, here's the temperature. If I make this bigger, I'm subtracting a negative number, right? So overall, as this gets bigger, it's making delta G more positive. And if you have a hard time thinking about stuff like that, well, what you can do is say, well, I'm going to just plug in a number. I'm going to say, well, let's say that it's 398 instead. And I'm just going to calculate it. Negative 137.5 times 10 to the 3 minus 398 times negative 120 gives me negative, so at 398, delta G is negative 89541, which is negative 89.5 kilojoules. Is it getting more negative or more positive? It's getting more positive. So as the temperature increases, increases, this is becoming less spontaneous. At some point, it will become non-spontaneous. Any questions?